Hello, everybody. Thank you for being here. We are the Embry-Riddle Aeronautical University Solar Studs, and we are presenting our submission for the Solar District Cup 2021. Oh, there we go. Sorry about that. So here is our team structure for the Solar Studs. My name's Jennifer, and presenting we have Elijah, Eric, Audrey, and Ray, and we also have Ian and Dr. Campier in the audience joining us. So we were given the University of Nebraska-Lincoln, or UNL, as our district for this competition. UNL is a large public university that's located in Nebraska. If you look on the map that's on the slide, the Global Horizontal Solar Radiance Map, or GHI map, you can see that Nebraska's UNL is getting about 4 kilowatt hours per meter squared per day. GHI is a measure of how much energy from the sun we can use. And you can see that UNL gets about less GHI than other locations in the US. UNL also wants to promote clean energy and sustainability on their campus, and they're doing that through the Chancellor's Sustainability and Resilience Commission. So how do the Solar Studs create their design? We focused on the 3 C's: clean, cost, and core and unity. Core and unity is a term that our team dubbed as a community for UNL's campus. So for clean, we're incorporating solar power onto the University of Nebraska-Lincoln's campus. For cost, we're going to design a cost-efficient system that's cheaper than the current non-renewable energy utility. And for core and unity, we're going to engage the UNL community and campus-wide sustainability efforts. I'm now going to pass it, by designing PV systems, designing battery resiliency systems, analyzing our systems, ensuring compliance with the master plan, and demonstrating financial viability, we together can create a corn unified campus. I'm now going to pass it off to Elijah to take a deeper look into our systems.
Yeah, thank you, Jen. I think an important note to make about UNL's utility system is that Nebraska is actually the only state in which all electricity providers are publicly owned utilities. And you can see the effect of that for UNL's energy charge. They're basically being charged an average of about 2.5 cents per kilowatt hour, which is extremely cheap energy. And in looking at the comparison between UNL, the rest of Nebraska, and the US, this difference is just astronomical. UNL really is only being charged 2.45 cents per kilowatt hour. So how can we design a profitable photovoltaic system if energy is this cheap for this university? Well, we'll tell you how. We plan on attacking the demand charge. From the demand and facilities charge for these buildings, UNL is being charged in excess of $21 per kilowatt per building per month of their billing demand. That means that this is the opportune place to be able to use solar and battery storage systems to achieve cost savings for the university. So, in summary, the Solar Studs design hits the 3 C's. First, we have a clean design. We achieve 5% yearly energy offset with a total system size of 880 kilowatts. We also sustain a 3-hour resiliency challenge outage with 95% confidence. For cost efficient, we have an $180,000 total project MPV, an IRR of 7.52%, and a payback period of just over 11 years. And in terms of core and unity, we comply with the Chancellor's Commission, or CSRC. We have the dubbed Warren Buffett Solar Center, named for one of UNL's most prestigious graduates, agrivoltaic research stations to engage the undergraduate and faculty community, and solar signage all around city campus. All in all, we put the corn in the Nebraska Cornhuskers. So let's take a tour of our proposed systems. First, we're going to look at East Campus. Our 5 independent systems here are colored differently. Let's take a deeper dive. First, we have our Northwest Carport. This 205 kilowatt system provides power and energy to 11 different buildings on East Campus. This ground-mounted carport also comes equipped with EV charging to promote sustainability, even for all the students that park under it. Next, we have our Resiliency Challenge location of the Animal Science Complex. Here we have a 206 kilowatt PV system. This is split between rooftop mount and a ground-mounted carport, also included with EV charging. Finally, we have 3 separate self-contained rooftop systems, the first of which is Law College. This rooftop system provides power and energy to Law College's loads as well as charging its battery. Next, just to the south, we have Barkley Memorial Center, a system size of about 22 kilowatts, and again with an associated battery storage system. Finally, we have a College of Dentistry system with about 40 kilowatts and another battery storage system associated with it. Next, we're going to look at East Campus. I think what's going to stand out is that corn on the rooftop, and we're going to touch on that a little bit later. But first, Andrews Hall is a standalone rooftop system that's providing energy and battery storage to that system there. Next, we're going to have solar signage pole mounted at eye level in and around city campus, layered with solar skin to provide opportunities for university signage, maps, logos, anything of that nature. And finally, we have what we like to call the corn. This is a rooftop mounted system providing 75 kilowatts of power to the city campus, allowing it to charge batteries for different buildings and provide loads and peak shaving to different buildings around the campus. Finally, we have the agrivoltaic field just east of East Campus. We have 3 separate agrivoltaic research stations, all ground mounted. These are placed in the grassy areas close to crops so as not to disrupt already existing crop structures. Again, we have 500 panels, 141 kilowatts there, and opportunity for research for both undergraduate, graduate, and faculty members. And finally, we have the Warren Buffett Solar Center. This is an ideal solar roof area. This is our idea of engaging the UNL community with local farmers markets, movie nights under the stars, anything of that nature that we can engage UNL's surrounding community with to increase viability for the project. And I'm going to pass it off to Jen to talk more about the details of our agrivoltaic systems.
So agrivoltaics is a symbiotic relationship between agriculture and photovoltaics. If you see in the first image in the top, you have 2 lands that are being used for separate uses, and you get moderate yields from them. However, if you combine the lands and use them for the same use, then you get better yields. That's the basis of our agrivoltaic research stations. Also note that different crops require different amounts of light. So our team designed 3 different research stations with 3 different varying amount of sunlight. So that can be a way for students and faculty and anyone on the UNL community to use that as an opportunity for research. So for the first research station is 2 feet of spacing, and it's used for vineyards, beans, and oats. The second research station is 4.17 feet of spacing, and that's going to be used for wheat and vegetables. And then our last research station has 6 feet of spacing, and that's going to be used for corn. I'm now going to pass it off to Ray to talk about our resiliency challenge.
Okay, so what is resiliency? Resiliency is the ability and capacity to recover quickly from difficulties. In this essence, the solar and storage system is to supply enough power to sustain enough energy or power during a power outage. Now, for this challenge, we were giving a requirement of 30% of animal sciences load profile given at any time, which would be classified as the critical load. This is important to know because in this building, the University of Nebraska contains about $2 million worth of inventory. We need to create a system that is reliably going to support 30% of its loads during any time during the year with a power outage. Now, we decided to choose a 3-hour power outage, which is a once in a lifetime opportunity during the 20-year lifespan of the project, compared to the regular outages you normally see within Nebraska, which is 20 to 30 minutes. So in our decision process, we decided to keep a 3-hour outage for the once in a lifetime event. Now, for each of our systems, we have our solar panels, inverters, and then we have 2 different types of residential batteries. The reason for the 2 different types of residential batteries is because for each building, we had a certain sweet spot where we didn't want to add 2 of the same batteries, but more find a different capacity battery. In most buildings, financially, we're better to keep an energy capacity between 10 and 12 kilowatts. So for our resiliency battery, we decided to go with the Tesla Megapack. We decided we want 4 of these Tesla Megapacks with certain specifications, such as a power rating of 50 kilowatts and an energy capacity rating of 200 kilowatts with 100% depth of discharge in order to meet the 3-hour power outage and its functionalities. Next slide. So our expected operation would be peak shaving. Most of our solar panel, or most of the peak shaving method is achieved through solar panels, as most of the loads happen during the day. And then we have on top our residential batteries. which will shave off another 5 to 10 kilowatts based on the very max charge each month. And this is chosen not only based off of REOP Lite, but also MATLAB simulation to find the correct amount to peak shave.
So when conducting our distribution system impact analysis, our two main metrics of interest were voltage constraints as well as equipment overloading. Voltage regulation is an important power quality key performance indicator because violating voltage constraints causes things like insulation damage, reduction in equipment lifetime, as well as increase in operation and maintenance costs. And we also wanted to avoid equipment overloading because frequent overloading of electrical equipment can lead to premature aging and reduced lifespan. So our first step was to evaluate the base case. We discovered it was a three-phase system with 277/480 volt transformers, provided the current yearly loads for East Campus as well as all the existing lines. Our next step was to implement the proposed system. We modeled the PV systems using NSRDB irradiance and temperature data, as well as creating P versus T and efficiency curves for the systems. Each PV system was routed to their specified building to optimize peak shaving, and the 4 agrivoltaic systems were wired to the transformer required by the rules. The storage systems were then modeled using dispatch profiles following a peak shaving algorithm and are located in each building. After that, we conducted a sensitivity analysis. We chose 4 different scenarios with varying PV and loads to test the distribution system under high stress scenarios and ensure that the constraints were met. Finally, for equipment upgrades and additions, the agrivoltaic field transformer was required to be upgraded from 150 kVA to 500 kVA to support the new systems in the agrivoltaic field. And we added new lines as well as smart inverters to the carport system.
So some of the financial inputs for our solar plus storage system include a PV capital cost of $1,600 per kilowatt, commercial battery costs, residential battery costs, and tax incentives, for which we use the 26% federal ITC. And then for financial outputs of our solar system, that included a PPA price of about 12 cents per kilowatt hour. And then for the solar plus storage system, we had an NPV of $187,831, a IRR of 7.52%, and a payback period of 11 years. For the resiliency challenge, because of the amount of solar that was used, it had initially a negative NPV of $332,853, and it has an avoided outage cost of $2 million. So with this, we have a positive NPV of over 1.6 million.
The development plan outlines the important steps that our team needs to make to construct a proposed system. So the first part is to site plan where our proposed systems are going to go. So UNL is located in Lancaster County and it's under the Lincoln 3-mile jurisdiction. So it's zoned for public use, P for public use, and it must follow the Lincoln Municipal Code Title 27, Chapter 27.59. Next, you need to get the necessary permits and documentation that's crucial for this project. This includes building, demolition, electrical, and height permits, as well as being in compliance with all local, federal, and national building codes. Then our team proposes systems that were in compliance with UNL's master plan called Plan Big, which provides oversight for the university's growth over the next 15 years. As you can see on the image, our East Campus proposed systems do not interfere with Plan Big. And lastly, our team identified potential risks that could delay the development plan. These risks include low temperature, tornadoes, and floodplains. These risks should be acknowledged when in the construction phase of the development plan. What drove the solar studs to create our design is UNL's devotion to community and sustainability. Our proposed systems, such as the Warren Buffett Solar Center and the Corn, will bring the community together in a new and greener way. Thank you. We'll now take questions.